Okay, so we've drawn this graph of y equals 2 to the x, so keep that picture in your mind. And then we're going to look at some of the important features or characteristics of the graph of 2 to the x. So the domain is all real numbers, or you can write it in interval notation as negative infinity to infinity. Then the range was we only have positive values of y. So if you write that in interval notation, it will be from 0 to infinity, but we can never get to 0. There is no value of x you could put on 2 to the x that would make the result come out 0. Then x-intercepts, we didn't have any. We never touched the x-axis. And then every exponential graph is going to have a y-intercept of 1. If you see y equals a to the x and you put 0 in for the x, you're always going to get 1. So let's come back and look at the graph and talk about end behavior. So as x is going to infinity, y is going to infinity. But then as x is going to negative infinity, y is getting closer and closer to 0. So that's the end behavior with arrow notation. So since this function is always increasing, we know it is monotonic. And because we know it's monotonic, we know it's 1 to 1. So then we know it has an inverse. Because previously we had a theorem that said if a function is 1 to 1, guaranteed it has an inverse. So this is how somebody a long time ago said, look at this exponential function. It's always increasing. It must have an inverse. Let's call that thing the logarithm. And that's going to be the next thing that we learn about. So lots and lots of things grow exponentially. We've been watching spread of a virus grow exponentially. Learning happens exponentially and forgetting also. So lots and lots of things are described with exponential functions. So now here are some graphs, and let's look at what we can tell about how they've been transformed from a parent graph. So all of the basic exponential graphs have this same shape. So the fact that this first one is reversed around the y-axis means it must have been 3 to the negative x. Because the parent graph, you can see all the choices here have 3 to the x as the parent graph. So then number 38, I can see that it has the point 1, 1. So it looks like the point 0, 1 moved over to the right by 1. So that would be moving to the right is subtract 1 from the x before I do the exponential function. So look and make sure you agree that when x is 1, that gives us the right result, and when x is 0, that looks like it gives us the right result. Okay, then 41, this is the parent graph. If you look at it, it has the point 1, 3 and 0, 1. And then in 42, we're reflected around the x-axis, so the negative happens after the function. Okay, then here is make a list of the transformations and think about how that changes, if any, the domain, range, and horizontal asymptote of the function. So this first function we have shifted down 2 from the parent graph 3 to the x. So for A, we'd say the domain doesn't change. That's still all real numbers. Shifting a graph up and down does not change its domain. Then the range, though, shifting the graph down to changes the horizontal asymptote. So now the graph can get down to -2 in the y direction and then still goes up to infinity. and that makes the horizontal asymptote also shift down to y equals -2. Okay, for b, we have 2 being added before the function, so that's going to shift left 2 units. And shifting right and left doesn't change the domain. And shifting right and left doesn't change the range either. So the range and the horizontal asymptote stay the same. Okay, then let's look at C. And after the function happens, we have a negative. So that's going to reflect about the x-axis and then shift up 1 unit. So here's our basic graph. We're going to reflect it about the x-axis and then shift it up 1. So here's the new horizontal asymptote. Y equals +1. Domain doesn't change, but the range now is from -infinity up to 1. Okay, and then the last one here we have, let me break it down, and I'm going to write it as -2 times -1/3 times x plus 1. And that's the same thing, right? I just wrote it in a little bit different way so that I could analyze it more easily. So the first thing that's happening is a 1/3 is multiplying the x. This is happening before the function, so it's that counterintuitive one where you might think it's compressed, but it's going to be stretched by a factor of 3. So it's going to actually stretch it out. So that's the first transformation. Then we have this negative before the function. That's going to reflect about the y-axis. Then the function happens. Then we have this negative out front, and that reflects about the x-axis. And then the last thing we have happening is shift up 1 unit. Okay, let's just take a quick look at Desmos so you can see the graphs. And here is the graph of 2 to the x. And then here's 2 to the 1/3 times x, and see how it stretches the graph out. So that's, to me, completely counterintuitive, but I just have it memorized as it's counterintuitive. Then if I do 3 multiplying the graph, the x before the function, it horizontally compresses the graph. Okay, so the number e is the last thing we need to talk about, and it's the number that this expression approaches as n goes to infinity, as n gets larger and larger. So in calculus, you'll write this with limit notation as you write LIM, then below LIM you write the limit of what, and so it's as n goes to infinity, of 1 plus 1 over n to the power of n equals this number e. So it was a number that already existed. It just kind of got discovered by a mathematician named Euler, a Swiss mathematician. So the letter E was chosen to represent it in his honor because he kind of discovered the idea. E is an irrational number. So it doesn't have an exact decimal representation, but you can see by this chart as n's getting larger and larger that you're getting closer and closer to some particular number. But there's no end to the number of decimal places you can get as n gets larger and larger and larger. So there is no exact decimal for e. just like there's not for the square root of 2 or pi or any other irrational number. So I want to make sure you know where the E button is on your calculator. So let's just check and make sure you're getting about 3.320 for the first one. And then about 149.952 for the second one. And we use the wiggly equals to say we're rounding here. Okay, then a couple more transformations using the E for the base. And the first one is going to be a reflect about the y-axis because it's happening before the function. And then we're going to have a reflect about the x-axis. Then for B, again, I'm going to write it in a little bit different way so I can see what's happening easier and analyze it. So the first thing I'm seeing happening to the x is multiply by 1/2. So this is going to cause a horizontal stretch by a factor of 2. Then I have a multiply by a negative before the function happens. So that's going to reflect about the y-axis. Then I have a negative after the function, reflect about the x-axis. And then last we have shift up 9 units. So in this section, we're going to solve some simple exponential equations using the idea that says if you have two bases that match and they have exponents that look different, really it has to be true that the exponents are also equal. So the idea is that you try and write your quantities with the same base so that you can equate the exponents. So this first one, I would rewrite 81 as 3 to the 4th power, because then I could say, then it has to be true that negative x equals 4, so x equals negative 4. Then for the next one, I can see a way to write each of those bases as 3 as the base. So I rewrite 9 as 3 squared and 27 as 3 cubed. And then I recall the property of exponents that says I should multiply the exponents. And now we know that 2 times negative x plus 15 has to equal 3x. And we can solve this. Negative 2x plus 30 equals 3x. 5x equals 30, so x equals 6. Okay, then C is pretty easy because the base is both e, so we know that 3x equals 2 minus x, or 4x equals 2, which I know then means x equals 1/2. Okay, then D is kind of a think about it question. If I have 3 to the negative x equals 2, and I want to know what 3 to the 2x equals, well, one way to do that is to bring both sides to the power of negative 2, knowing that on the left we would multiply the exponents, and that would give us 3 to the 2x is 2 to the negative 2, also known as 1/4. Okay, then we have a graph to figure out what the exponential function is, and we're given several points that are on the graph. Well, we know it needs to look like f of x equals ca to the x. So let's use this information that when x is 1, y is 5. So I know that CA has to be 5. Well, now let's use this information that f of 0 is CA to the 0, and that has to equal 1. So C equals 1. So then I know A equals 5, and f of x equals 5 to the x is the equation for that graph. Okay, and then the last one, again, we're given some points, but we need to think a little bit here of, we're going to have a horizontal asymptote of y equals -3, have the point 0, -2, and the point -2, 1. So I have to approach this horizontal asymptote. So I know my graph has to be going something like this. So it's clearly been shifted down 3. So I can start with f of x equals CA to the x minus 3. Then let's use our information of when x is 0, I know the y value has to be -2. So c minus 3 is -2, so c must be 1. So now I know f of x has to be a to the x minus 3. And let's use our other piece of information that says f of -2 is a to the -2 minus 3, and that has to equal 1. So a to the -2 has to equal 4. So 1 over a squared is 4. So that means 4a squared is 1, and a squared is 1/4. So a has to be 1/2 because a, the base, has to be bigger than 0. So now we know f of x is 1/2 to the x minus 3, and you can check and make sure that that agrees when you have x is 0 and x is -2, and then as x gets large. And that's all for this section.